I'm Anil Kumar, and in this video we will summarize the strategies which we have learned to evaluate limits. So we have a couple of the strategies. One is direct substitution. So I'll make some bullets here and then we'll fill in the different types of strategies which we have learned. So one of the first strategies which we learned was direct substitution. Now this strategy really works when the function is continuous, right? So it works in continuous functions. Now whenever you do direct substitution, at that time what you notice is that the limit is equal to the value of the function at a. So what we are considering basically is limit of the function as it approaches a. So limit when x approaches a for a function, I should have written f of x also here, is equals to f of a whenever you do direct substitution. Now that strategy works, as I said, for many examples where especially we are considering polynomials. So all polynomials, it works. Absolute functions just alone, right? Alone. If you combine, then it may not work, right? And sinusoidal functions, it works for exponential functions. So for all these functions and many others, you could define your own. Direct substitution works. Direct substitution also works for rational functions in case we are looking for limit at a point which is not at the point of discontinuity, right? So at times it works there also. So if the point is in the domain of the function, it works. So basically what is important here is that a is in the domain and the function is continuous, right? So and the function is continuous at that time, right? Domain and continuous. Well, when I say domain, it has to be continuous. Well, the key is that the function should be continuous at a to directly substitute and get the result. When this strategy doesn't work, then what really happens is that when you directly substitute, let me draw a line here and then we'll move further. So what really happens is when you directly substitute, you may get 0. Till then it is okay. But if you get 0 over 0, then we say it is indeterminate, right? So these are the cases when it is indeterminate. So when you get 0 over 0 form, then we apply many different strategies so that the common factor which is making it 0 over 0 can somehow be cancelled out and then substitution is followed. So we try to write an equivalent expression and then substitute. So that is the strategy. And for that, how can we get rid of that common factor? For that we have different strategies. One of them is factoring. One is rationalization. And one is substitution of variable. So these are very common strategies, or we can say change of variable, which are applied to find the limit of a function in such cases. So what I have is, I have about hundreds of videos on this topic, and I'll give you links so that you can follow those and understand and practice each kind of evaluation of limits. In factoring, for example, you could find the limit of the function as x approaches, let us say, 7. And since I wrote 7, I'll write x minus 7 in the denominator. And if I substitute 7 here, we are going to get 0 in the denominator. And in the numerator, let me write a factor which has 7 in it. So x square minus 49 could be a good substitute. So that could be an example of factoring. You can factor and then get rid of common factor, get your answer, right? At times, we could have questions like x approaches, let us say 4. And in this case, I'll use square root and we'll say square root of x minus 2 over x minus 4. So in this case, you can do factoring. Let me take a cubic example. X cubed minus 27 divided by, let us say, 3 minus x. So I flip this, you'll get negative result. So we have limit x approaches. I'm equating x to 3. So 3 minus 3 will be 0, right? 3 is a common factor in the numerator also. So those could be your examples for factoring to try, right? So these are good examples. You can always try them out for practicing. I'll also provide you with some links where they can help you to solve, right? Now let's take rationalization. So when we take rationalization, we normally take a square root function. Those are the best options. And square root functions, we could rationalize numerator or denominator. At times, we could rationalize both. So let us have x plus, let us say 16. Square root of 16 is 4, so I'll take away 4 from here. And okay, that makes it 0 and x. So x equals to 0. That could be a good question to work with. Rationalization, right? You could actually solve this question also by rationalization, multiply and divide by the square root and then solve your question, right? So that could be another candidate for rationalization. At times, we may have more complicated cases where rationalizations can work, but I'm listing simple ones here, and I'll give you link for the difficult ones later, right? So let me write one, and then we'll figure out what limit we should write. So let's have square root of x minus 2, and then we can have cube, okay. I mean x cube, I wanted to write x cube, okay. So we have x cube, and then root minus 8. Now in this case, if I write, yeah, that could work actually. So this could be 0 if I have 4, right? So 4 square root will be 2, 2 cube will be 8. So I can approach this to 4. So that could be a limits question where you need rationalization, right? We could also have questions like, let me give you 2 radicals now. So we could have x approaches in, let's say 1. I'm not taking cases of infinity at present, and we'll take them later. So we'll have x, let us say x plus 3 minus, let us say 5 minus x divided by x minus 1. And this particular case, we have 2 radicals. You may have to rationalize and solve this question. So that could be another example of rationalization where you may rationalize. I'll give you links where rationalization of both numerator and denominator may be required, right? And now let's take some examples of substitution. Now remember this thing, all these questions which I have written could also be used by substitution, all right? So you could follow substitution techniques. Simple ones could be, let's say x approaches 1, let me write minus 1 here, and x to the power of 1 over 6 minus 1 over x. So if I write plus minus, so minus is a factor, so I'll write plus 1 here, x minus 1. Okay. Now if I write 1 here, I get 0 here, 1 here, I get 0 there. So it is a 0 over 0 candidate, right? It's a good candidate for us for substitution, right? So likewise, we can actually write many different functions where substitution could be a good technique to follow, right? And then find our answers. So I like you to explore some of these functions, and then also you could pick up some functions from here and apply the strategies. I left this space because I thought I will add few more strategies which are kind of related. One of them is, I should not say strategies for limits, but other kinds of limits, right? So one, we also discussed about one-sided limit, right? One-sided limit. So many times when you need to evaluate limits, you have to evaluate limits from both the sides, and limit is possible at a point if both limits from both the sides is same. So that is kind of very important to figure out. And we also use graphs to find the limit of the function, right? So these are also the strategies which you should be considering. For example, we could have a graph here. Let's draw one, and let us say here is we have a parabola which is kind of like this, right? And then we have a function which is kind of like this. Now in this case, let us say this point is 1 for us. Right? We could find that the limit does not exist at 1, since there is a jump discontinuity, right? So those kind of questions you could work from the graph. So overall, what we learned in this particular chapter is that limits could be evaluated for each and every function. There could be different strategies. If the function is continuous at the point of our interest, then we could just substitute and find the answer. If it is not continuous at that point, then we may have to follow one of these strategies. Factoring, rationalization, substitution of variables, these are the standard strategies. Normally, for rationalization, you have radical signs which need to be rationalized. Now, you could also have piecewise functions where you'll be interested in one-side limits. So let me say piecewise functions. So we explored one-side limits for many functions. Especially good examples here are combination with absolute functions. So absolute combination. Now whenever you have combination with absolute function, it becomes a piecewise function, right? So that could be a very interesting example to work with, and you can of course combine any of these with your polynomials and make your own piecewise function to find limits at different points. With this, I think you get fairly good idea about how to evaluate limits. We'll have another video on evaluating limits at infinity that we'll treat as separate chapter, and I hope with that we should be in a good position to move on. Thank you and all the best.